Margaret Lloyd. She gave a talk last week, excellent talk on cover crops. So you need not much introduction, but she's the small farms advisor for Yolo, Solano, and Sacramento counties. Okay, Margaret, take it away.
Great, thanks, Joji. What a great talk, Mike. Thank you so much. Okay, so today I'll be talking about estimating N availability in compost. And so composting is achieved in a variety of manners, as many of you know. So from static aerated piles to windrows to top-fed vermicompost bins. And in this process, most of the decomposable or mineralizable forms of nitrogen are converted to more stable forms or lost as ammonia gas. And so it reduces the mineral N content and increases the stability of the organic matter. One way to study the compost N mineralization is through soil incubations. And to do this, the compost is added to field soil. And in this case, with the work that we did, we added it to organically managed field soil from local farms and incubated it in optimal temperatures and moisture for 12 weeks. And Patricia will describe this a little bit in more detail in her next presentation. But so what we learned from this process, we took multiple types of compost, those based from poultry manure to yard trimmings to mixes of the two of those. We had some vermicompost. And this is what we found. We found that the composted, we have simplified here, the composted poultry manure had some readily available nitrogen at the beginning. So if you look at time zero on the bottom x-axis, you have the time, and on the vertical axis, you have the available N. So you can see that that composted poultry manure had some initial nitrogen available. And you sort of see these two phases looking at that composted poultry manure. And you'll see this with amendments that Patricia will talk about next, the sort of initial, somewhat rapid release or available release, that sort of steep curve, and then a second, more slow release rate. And so when you look at the end of 12 weeks, so that would be, about 3 months, you can see that somewhere around 30–35% of the total nitrogen that was in that material became plant available. And when we look at the composted yard trimmings, it's hovering around zero. So there was little to no to even tied up nitrogen from that type of material. And composts are sometimes applied to supplement the soil nitrogen. However, if that is really the goal, the nitrogen availability from these materials differs widely. And so here's just a table form of what we just looked at with a little bit more information. We present these two types of composts, a yard trimmings based and a manure based. And you can see what the typical percent nitrogen is from less than 2 to more than 2, what that C to N ratio looks like. So the yard trimmings was in the range of 13 to 20, and the manure based compost was 6 to 8. And then that nitrogen availability after 12 weeks. So thinking about from a nitrogen standpoint, the yard trimmings compost is going to be providing nitrogen in a long-term sort of years time frame, whereas the poultry manure compost is giving some of the nitrogen in the near term, in the weeks to months time frame. And what we found was that the carbon to nitrogen ratio of an organic substance, and especially its degradable fraction, is the decisive factor for N release from organic matter. So this was a really important predictive factor for how to estimate what you might get from a material. So here is a figure. On the x-axis on the bottom here, you can see the carbon to nitrogen ratio. And on the vertical axis, we have the available nitrogen across 12 weeks, at 12 weeks. And that's percent of the total. And so what you can see here, so the two composts are these red dots and blue dots. And you can ignore the other dots for now. We're going to look at those during Patricia's talk. But so the red dots are here, and the blue dots come right across the zero line. And you can see that this curve crosses somewhere between 15 to 1 and 20 to 1. So this becomes an important threshold to make note of for where N immobilization could be occurring with a compost. So this means that it's not going to be a source of nitrogen, and it can even begin to tie up nitrogen from your crops. In the absence of a C to N ratio, the N concentration can be used. So this is the N concentration on the x-axis instead of the C to N ratio. And so if you recall, the plant-based compost was like 0 to 2% nitrogen, and the manure compost was in the 2 to 5 range. So you can see how they also follow a correlate well to a curve here, looking at availability by percent nitrogen. That being said, most compost suppliers are able to provide you with a C to N ratio. So on that note, a compost supplier will usually be able to share with you a soil test or a compost analysis. And this is what it might look like. So just to point out a few key points here. So in this analysis, this is a part manure, part yard trimmings based compost. And we have percent. So this is about 2% nitrogen. And note whether the report that you're getting is reported on a dry basis. If not, the calculation for moisture will need to be taken into consideration. Also, you'll commonly find this C to N ratio here. So with those pieces of information, you can, that's what they've done here is this calculation for pounds of nutrients per ton. So what they did was take the 2.09%, divided by 100 and times 1 ton of material, 2,000 pounds, and that gives this 41.8 pounds of nitrogen per ton. So that's the total amount of nitrogen in the material. How do we estimate plant available nitrogen? So I'm going to use these two figures that I showed earlier and walk through that. So we have a part manure, part yard trimmings based compost. And while this figure is simplified, we generated this figure from multiple types of compost, multiple batches of the same type of compost. And we found that it was quite consistent, and that if a material was roughly half manure based, half yard trimmings based, it really fell right in the middle here. So that's what we're going to do for this part manure, part yard trimmings compost. So we did this first calculation. We got the total amount of nitrogen in 1 ton of the product. So the next step is availability. That report showed 11 to 1. And this falls about right in the middle. And so just visually, I'm going to estimate that at around 15% of the total. You can also look at this table. 11 to 1 is about in the middle between these two. So I took about half of the poultry manure compost. Multiplied the total times 15% of the total to get about 6 pounds of nitrogen per ton material. So this is what can be expected in the following few months after application. Of course, this has to be calculated by the amount applied. So I chose 10 tons per acre. So that gives me about 63 pounds of nitrogen per acre I can estimate will be plant available from this compost. one note is whether the material you bought was calculated by, was it tons per wet weight or tons per dry weight? So moisture can range from 30 to 60% of material. And so considering the actual application and making adjustments for the amount of nitrogen by dry weight is always the easiest. So here's another soil test that we can look at together. This is for spent mushroom compost. So the total nitrogen was 1.75%, so just under 2%. And they also have in this soil test ammonia nitrogen, and that was at 1.22 pounds. The C to N ratio is 22 to 1, so that's quite high, and we might expect some tie-up, and 58% moisture here. And in this material, they also provided bulk density. So if you're working on a cubic yard calculations, this can help you make that conversion from tons to cubic yards to tons, so that you can work in the pounds per acre, tons per acre conversion. And the reason that I bring up the ammonia is because that could be suggestive of how much nitrogen might be available immediately. So if you recall that the poultry manure did have some more immediate nitrogen available, that can be interpreted somewhat from having a number like this on a soil test. Now, this is a very small amount in this case, so I would not be expecting much from this compost in terms of nitrogen. So one comment is that high mineral nitrogen contents usually lead to good short-term and availability. So following up what I sort of just talked about, and here's that starting point for this composted poultry manure. So looking for that piece of data in a soil test can help you refine what you might expect in the short term. So if only a small part becomes available each year, how much is ultimately available? And what's that N accounting over time? This is a really beautiful visualization of that cumulative impact of annual composting. So let's follow the blue color. So each of these colors represents a compost addition. So year one, we add compost, and we can expect about 33% of that total N, the N mineralization, from that compost that year. The second year, that material remains in the soil and is going to be releasing an estimated 16%. The third year, an additional 9%. And in this way, you can see how this material is providing a sort of background contribution of nitrogen to the system. Because in the second year, then, you're going to add another 43 pounds of nitrogen per acre from a manure-based compost. And then you add another 43 pounds of nitrogen per acre of compost. And so by adding it each year, you can see that there's this cumulative effect of nitrogen benefit and release. And after about 4 years, you can see it sort of reaches a steady state. And some of you, I feel like I have often heard about when folks are transitioning from conventional to organic farming, there's sort of there's this transition period. And there's a lot of things biologically that are getting sorted out during that time. And I feel like this visualization is a way to understand some of what might be happening with the nitrogen cycle in the soil during those early years of a transition, or even just starting to use compost. So the full benefits take several years to accumulate and start to reap the full benefits. And if you recall this visualization, this figure from last time, in which we talked about all the contributions of nitrogen from multiple inputs. And so this blue band represents the compost addition. And you can see here that it's about 40 pounds or so we're expecting from this compost composted manure. And so that what I just showed about the accumulated effects over time, that's coming from the soil organic matter. And so in a way, you know, when we think about the soil organic matter band, it might be like a rainbow of bands, because it's releasing nitrogen from all these different things that have been happening over many years. And one of those being the repeated application of compost over time. And so after the long-term application of compost, the overall end use efficiency, when it's compared to a mineral fertilizer equivalent, is typically reported in the range of 40 to 70%. And so that's thinking about the bioavailability. And it's often assumed that the mineral fertilizers are usually at 100% availability. Another way to think about this and look at this is in these sort of active pools and old pools of soil organic matter. And so when we look at the age of residue, that can be crop residue, compost, we'll see that in those first years following incorporation, they can be considered in this active pool of soil organic matter or of organic matter. This is going to be our crop residues, manures, compost, cover crops, and they're going to be continually releasing and breaking down, similar to that stacked bar chart showing the compost over time. So you have these active pools for the first 4 or so years, and then they become these very stable forms of organic matter that are very slow to break down. And I could end this talk here because this really covers the basics and the drivers and the nuance of some of the availability. Because once we go on beyond that, it's kind of like opening Pandora's box. The variability in feedstocks, compost age, compost maturity, moisture, compost process, they all become variables that influence this wide variability that many of you might be familiar with compost. So that being said, I will cover a couple more points, but I really want to emphasize that you can go a long way with understanding what to expect from a compost with just knowing the C to N ratio, and then some of the additional information can help with some of the detailed nuance. So what makes compost different from crop residue and even other types of amendments? The main difference is that during composting, the easily decomposable or labile materials are eliminated, and what is left is a more stable form of carbon present in the compost when it's applied. And so materials such as food waste, biosolids, or manures are rich in fats, sugars, starches, and waxes. And these labile forms are quickly converted by compost microbes to CO2 and water, and they leave behind recalcitrant resistant materials such as wood, and these tend to contain a lot of cellulose and lignin. And it's common for these initial labile materials to generate odors, to tie up nitrogen, to release phytotoxic compounds as they break down. And because of all this activity associated with the biological breakdown, the most direct means of assessing a compost stability is to evaluate the rate at which CO2 is produced as the material breaks down under controlled conditions. So this resulting material One of them is lignin, and lignin is very tough to decompose. And I have this image here to show how complex lignin is. And it's the second most abundant component of plant residue in terrestrial ecosystems. And by itself, it's relatively recalcitrant. And degradation rates are negatively correlated to the lignin content, or the lignin to N ratio. The purpose of lignin is it serves as this cement between wood fibers, as a stiffening agent within the fibers, and as a barrier to enzymatic degradation of the cell wall. And so one tangible way to identify lignin in your compost is how tough that material is. Can you tear it? And, lignin forms a physical barrier by attack from enzymes, and it reduces the accessible surface area of cellulose. And so it's very slow to decompose. And in addition, in order for it to decompose, it often has to have a co-substrate, carbohydrates. And so there's multiple reasons why lignin can be hard to decompose. And when microbes do decompose it, they basically break it into these smaller molecules, complexes. And so one reason why some of the high nitrogen products may have lower availabilities is the amount of lignin that is in that material. Now, this is still often embedded in the C to N ratio, but it can be an added factor for part of the slow release of a material. And so the higher the lignin fraction, the less mineralization will occur. Now, here's an example. If we compare alfalfa pellets, which have a pretty high lignin to N ratio, compared to partially composted manure. And so these alfalfa pellets are going to have less N availability relative to this partially composted manure. And if we look at blood meal, it doesn't contain any lignin. So a couple more thoughts. Composting plant residues increases that lignin content, and it decreases the sugar and lipid contents. And in this study, what they found was that the labile portion of the plant residue was significantly decreased from 30% to 9%. And what this is doing is this is decreasing the energetic compounds for the microbes, the sugars, et cetera. And so there's less available for the microbial food. Composting plant residues increases by threefold their residence time in the soil. So that material is going to stick around longer and be part of that active but slower pool of release over time. And lastly, the addition of fresh plant residues causes a priming effect, but compost residue does not. And that priming effect is that initial sort of flush of activity when material is added. It's a stimulation of the native soil organic matter degradation. And so what you can see here, this is total CO2 evolved. So this is somewhat representing like the microbial activity when material is added. And so here, this is non-composted plant residue. The darker circles are composted plant residue, and this is the control, the baseline. So you do see an increase, but not as much of an increase comparing compost to plant residue. And this is another visualization showing plant residue mineralization, the percent of the initial. So you can see this is less than 40% of the initial amount was mineralized compared to the non-composted plant residue. And the last point is that the amount of liquid contained in the compost affects the concentration of nitrogen per ton. And that mineralization of these organic materials is mediated by bacteria and fungi. And so the soil moisture will regulate that oxygen diffusion in the soil, with the maximum aerobic microbial activity occurring between 50 and 70% of water holding capacity. So moisture will influence how much one can expect from their compost. So to summarize, these two figures, whether you like to read it as a table or see the curve, are very useful tools for just that baseline understanding of what's the important C to N ratio or percent nitrogen of a material that can help you predict what you might expect for the nitrogen contribution. And 15 to 20 is that threshold for N tie-up. Second, that high mineral nitrogen contents usually lead to good short-term N availability. Third, the lignin to nitrogen ratio is negatively correlated with N mineralization rate. And that there's a big difference between adding fresh plant residue, which causes that priming effect, but composted residue does not. So thank you for your interest and attention in compost and nitrogen mineralization, and I'll take any questions.